Alright guys, this is Chalk University continuing our examples with linear equations and matrices. A little bit of not the curveball on this one. What do you do when you have two equations, three unknowns? Now right now we're not going to get too much into this. It will pop up again mostly in matrices, and there'll be different answers for that, but this one's going to be pretty basic on what we want to do. Again, like I said, I always try to outline the steps that we need to take, and we're going to follow these steps to try to solve for an equation such as this that I've given you an example for. Alright, so our first step when we're given these two equations, we have to solve for one variable which has two unknown variables within itself. So what do I mean by that? Well, essentially what we're going to be wanting to do is we're going to want to solve for one variable, and that variable will be in terms of any other two variables. So if I'm solving for x, x will be in terms of y and z, or some form of that plus minus, whatever the operator will be in there. So we'll take these first equations again, just basic math right here. We're going to try to get rid of the x, solve for y, multiply the top by -2, and we're going to add that. Once we multiply that by -2, we'll add that to the first equation. So what we'll get there is -2x minus 4y plus 6z equals 8. And then on the bottom, you just copy the equation like it is. Minus 3z equals 4. Want to add that up again. These are going to go away. You're going to end up with -3y plus 3z equals 12. If we divide both sides by 3, you'll end up, if I just write it out, so I know some people don't like it when I skip steps. You're left with y equals z minus 4. And what did I do there? Once I basically did that, I just moved over the BC, and that's what you'll get. And I moved over the y to make it positive, and so on and so forth, and then move the 12 over here to make it negative, so the 12 will become negative there. Alright, so that's our one part. We have y equals z minus 4. So what do we want to do for the next step? Well, what does the next step tell us to do? Plug the values back in to solve for the second unknown variable. So let's rearrange the first equation that we had, and if we rearrange, scroll right here, the first equation, what we're going to be wanting to do is we're going to be wanting to take everything from the x, since x is in single variables, and we're going to be wanting to move it over to that side. So essentially we're subtracting everything in here. So what you're going to end up getting is you're going to get x equals 3z minus 2y minus 4. Again, the 2y becomes negative, and then the 3 becomes positive, so that's negative, and that's positive over there. So that's our x variable. Now what do we want to do? We want to solve for the final variable, but we wanted to initially plug those variables back in. So what we want to do here is for y, we're going to want to plug in y right over here. This is step 2. So what do we get when we plug in y? Well, let's do it. We get x minus, or equals, sorry, 3z minus 2. And I'm going to keep this actually in the old color so you can actually visualize it better. Z minus 4. And then that's minus 4. So what do we want to do right here? Now we want to distribute the 2. Now a lot of people sometimes get confused on how to distribute the 2 if it has a negative. What I like to just do is put a plus negative and then just distribute the negative 2 all the way through. You'll get negative 2z. You're going to get plus 8 because it's a negative times a negative, minus 4. And then we have 3z, and that equals x. So what we want to do is we want to combine like terms. So for the like terms here, you're going to want to combine the z's and then the constants that we have over here. When you combine those, you're left with z plus 4 equals x. So now that was solving for our. Now let's solve for our final variable, which is step 3, which is z. Now, so what is z in this case? What we have to ask ourselves is, does this satisfy the equation? Well, actually, z is any real number, and that's all you need to know right now. I will do a proof for it in the next video for those who are more mathematically inclined and need to know everything. But just for the purpose of solving this problem explicitly, like, you don't really need to know. When it's any real number, that just means that you have infinitely many solutions. Solutions to the problem. So what does this mean? So let's say I plug in, like z equals 1 in this case. Well, in this case, you can double check me on it. It's going to be z equals -1, x equals 5, and y equals -3. And I can just keep plugging in values for z equals 2, and so on and so forth. You can just keep going on, and the answers will just follow. Like, there's no end to it. And what does this actually look like on a graph? And I'll be showing you this more in a proof later. But what this will essentially look like is when you have infinitely many solutions, you have a graph. Try to draw that as straight as possible. And you're going to have your two lines. You're going to have, let's say, this is line 1, and this is line 2. We'll draw it in black. Line 2. What this means is essentially that the lines are just overlapping each other. So at each point, there's a solution. And if you took a, like, let's say, a snapshot of this, and you blew it up a little bit, there would be infinitely many. So they just go on to be of infinitely many solutions. And that's what you need to know about when you have two equations, two unknowns. You'll probably end up for one of the variables having infinitely many solutions, and then you just back solve in that case. For matrices, this will have other implications, but we'll deal with that when we get there.